All right, guys, this is part 2 of our exam 3 for transport 1. In video 1, we did a proof of an expression, proof of a solution for our heat generation equation using our partial differentiation equation of our temperature with respect to time, which is equal to the thermal diffusivity times the second derivative of our temperature with respect to its position. And what we're going to be doing in this video is we're going to be deriving a forward differencing scheme to calculate our time varying temperature profile. So we're given a uniform bar with a 50 meter segment or 1 meter segments, and then we're given 50 meters as the length of the bar. So I just drew a little diagram here to show you how that works with our temperature coefficient right here. And what we're going to be doing in this video is using our temperature and its time with respect to its position, and we're going to be expressing the equation, our equation with our temperature. So basically, in our code, which we'll be doing in our next video, we're going to want it to choose a position in our bar or a segment. So pick a segment in our bar, and then this is how we're going to write it in our code so we can pick that position and calculate the temperature for that increment, and then for the next increment and the next increment. So here at time equals 0, we're going to have n our position is at 3, and then our time is going to be equal to 0, or that's backwards. Sorry. Our time n is going to be at 0, and our position at our time 0 is going to be 3. And then this is showing that at different times for the uniform bar, if we choose 2, it's going to be n equals delta t, j equal, or our position will be at 2. And this is just a metaphor for our code that we'll be doing. We just say that. Let's just say that's at time 1, position 2. Okay, and so now what we're going to do is we're going to express our partial differential equation using our temperature values. And so that's going to look like this. We have our time with our temperature at our beginning time minus at some position minus our initial position and time all over the change in time is equal to our thermal diffusivity times our temperature at n, and then our position plus 1 minus our original time and position all over the change in position, and then minus our temperature, our initial temperature, position, and time, minus our temperature and our position at the end, all over change in position. Okay, and so what we want to do now is we want to simplify our expression. All right, so our next step is just simplifying our expression. So we're going to get our temperature, position, and time increment of 1 by itself. So that's pretty self-explanatory. So it's going to look like this equals T, our initial temperature at time and position, times alpha, or plus alpha, plus 1 n minus T n J all over delta, or change in position, minus our initial time and position minus our last time and position all over the change. And then we're going to times that by delta T, which is our change in time. And we're just going to simplify this out further. We're just going to simplify this out further. This is going to be, excuse me, Tjn plus alpha, and we can rewrite this section and condense it a little by Tjn plus 1, or j plus 1, minus 2, so we're going to join these two together, Tn, is that right? Yeah, our initial minus Tn, our last position, and our uniform bar, and we can divide that by squaring our change in positions, and that is going to be times our delta T. Yeah. This guy. These are going to be on the outside of that expression. Alrighty, and then using our Crank-Nicholson's method, our expression is going to be, draw a little line over here. Our expression is going to be equal to our partial differential equation. So that is going to be thermal diffusivity times the change in time over the change in position squared. And so that's how we're going to plug that in for our code in the next video. And so to simplify this even more, we can just put in our R value for our expression, which will cover our thermal diffusivity and our change in time over our change in position squared. So we can rewrite this as Tjn plus R times T n J position plus 1 minus 2 Tjn minus T n J minus 1. And that is equal to this one. Okay, so we're going to be using this expression for our forward differencing scheme, and this is going to allow us to calculate the varying our time varying temperature profile in our uniform bar. We will be using this expression in our code and in our next few videos to solve our problem.